Sounds good. Only 25 minutes, but let's get started. So as Simon introduced, we're going to be talking a little bit about my favorite topic, which is data fetching unleashed. The story about Next.js, which was touched upon a little bit in the last talk, React Query and their BFF, and we'll shortly find out that BFF doesn't just stand for best friend forever. So a little bit about myself. I'll try not to spend too much time on it. My name is Faris, as I was already introduced. I'm an engineering manager, front-end subject matter expert, and also a conference speaker. Some of my previous experiences is working on connected TV applications, digital asset management, fintech, and also in fitness technology. So I've worked at companies such as Fit. I worked a little bit on projects with Discovery Plus, Eurosport, GCN, and then also a little bit of experience in the fintech world at a company called Navro. So what are my interests in the world of technology? I love web performance, and we're going to be talking a little bit about it today, along with architecture and engineering leadership. And of course, as software engineers love, I also contribute to open source projects, predominantly one called Raycast. Absolutely love it if you're a Mac user. It's a really great way to enhance your Spotlight search and get a couple of extensions that you can build in with React Native. Really, really recommend checking it out, and something I've been contributing to for the past couple of years. So let's set the stage about what we're going to be talking about today. So there's no one size fits all. Every project has its own unique requirements, and this talk is not about finding the one true way. We're just going to be talking about a couple of concepts. This is not a tutorial. We're not going to be building a full-fledged application, but rather focusing on patterns, things that we can apply to a multitude of projects. Everyone's going to be learning a couple of things today, and they're going to be having their own unique projects with their unique requirements that they're working at their companies or personally. And so we can't just copy and paste solutions there, but derive certain things and twist them in a way that they'll fit to the application that we're building personally. So this is not going to be a one-size-fits-all solution. And then also we're going to be looking at a couple of advanced patterns today. And there is such a thing as premature optimization. There are libraries that we're going to be using that are powerful, and it's important to understand if they're even needed in the first place. If you're building a simple calculator app, I don't think you need global state management and the most incredible, data fetching library and every single library under the sun. But it's really, as we move through developing an application, as the requirements develop, as it gets more complex, and as they scale to more users, bases with hundreds of users, thousands, millions of users, then we apply new strategies to solving those problems. And we're going to see through an evolution today of how to solve a problem that I looked at a couple of years ago. So what's the problem we're going to try and solve today? What challenges do developers, in particular front-end developers, face in creating a seamless user experience due to complex data fetching and management? So why bother looking at performance and how to do this really well? What's the point of user experience? Well, milliseconds are crucial for user satisfaction in the digital space. Quick load times are directly related to user happiness. Page load times that are in 0 to 2 seconds, which is considered the golden window, have the highest conversion rates, which is really what you're looking for. And then Google searches also show that around about 32% of an increase in the likelihood of a bounce rate when a page load time increases from 1 to 3 seconds. There's a source attached below for that. So the faster your website loads, the better experience the user is going to have. And that's not only about the initial load, but through every single interaction in your UI. If that reacts appropriately and the user gets the information they want, they see the data that they want to, then they're going to have a better experience. You're going to have better retention rates. You're going to convert them to paying users. And that's at the end of the day what you want, specifically if you're building a SaaS product, and even more so one that is SEO driven, one that people are just finding on Google. You're clicking on them. They don't know you. Your first introduction to a user is going to be on how well does your experience suit their needs, especially when you're trying to solve a problem that requires a lot of data fetching and a lot of crucial calculations. So what are the technologies we're going to use today? We touched a little bit on Next.js. If React is the library, then Next.js is the framework. If you haven't looked at it before, Next.js adds a little bit of interesting concepts into React's capabilities, such as server-side rendering, so you can pre-render pages on the server. You also have the ability to do static site generation, really good for content-driven websites or documentation websites. You've got file-based routing rather than using things such as React Router to manage things client-side, and then also API routes. So it's a full stack framework. You're able to actually design express API handlers into it. So it's all under one singular code base. Then we're also going to touch on React Query, which is a really powerful asynchronous state management library. And for those of you who looked at React Query, specifically look at the words powerful asynchronous state management. A big misconception with React Query is that it's a data fetching library. In fact, actually, it's not a data fetching library. It just so happens to be a state management library, which is really good at asynchronous tasks such as data fetching. So what does React Query give us? Automatic caching and background updates. Optimistic updates. That's when you send off a request, you already update your UI before you have a response from the server, and it really helps to do that seamlessly. Pagination and infinite loading. So when you're trying to get a lot of data from a server, you sometimes split that up and show that in different pages. That pagination is what that is, and that's what React Query helps us do sometimes. And then also prefetching. So when we're on the server and we want to prefetch some data before we show it to the UI, before the UI hydrates, we're able to do so. And then also query invalidation, a very complicated thing to do when you are trying to update your UI, and when you perform a task that invalidates data that was previously fetched. React Query allows you to link queries together so that if I perform action A, and then data set B becomes stale, I'm able to perform another fetch to be able to get that data again. So that just simplifies all those tasks of managing state and asynchronous work. So bare bones data fetching, we talked a little about the problem that we're working. So we're going to put ourselves in the box of a scenario. So I've worked in a lot of startups before, and startups, there are a lot of problems in terms of not everything is there and available to you when you need to solve a problem. So what is the problem we're trying to solve today? We've got a scenario. Imagine we've got a front-end team that needs to design a dashboard chart that displays the distribution of users' birthdays for the top 5,000 users in the system. What's our data source? The data is available via an API, which returns a list of users with all the data. So very typical scenario, we've got a GET request, and it returns a bunch of information related to users. Now, there's a limitation. To solve this problem, it's not so simple. The backend team is unable to provide a new endpoint. They're overcharged with work. They're unable to get to a point where they're able to provide you an endpoint, but the front-end team needs to still build this feature and get it shipped. So they're unable to also provide a data warehouse solution and the required data and the proper data format. So the data is going to come the way it's going to come, and it's not necessarily going to come in a way that's suited to the needs of our front end. We're going to look at a visual example in a bit. And there's a limit of 1,000 users returned for each request. So we saw a little bit in the scenario before that we need information display in a graph for 5,000 users. Each API request only returns 1,000 at a time. And so now we're faced with how do we build an optimal solution in a suboptimal scenario? So if we look at the architectural diagram over here, we can start to think about how we might build this application. We're going to start real simple. So I'm going to move my mouse. We've got a user over here. We have a user interface, which is our client side of the website that the user is viewing. And because our API can only give 1,000 data points at a time, we've got to make 5 parallel requests. So we're going to send off 5 requests at the same time from the client side. When we send requests, what's the typical thing that we do? We show a loading state. And while the loading state is happening, we can either receive an unhappy response or a happy response at 200. So let's say we receive an unhappy response. So we receive a 500 or whatever else, servers down, something like that is happening. Then we persist the loading state. We're not going to show anything to the user at this point, because what we're going to do is we're going to attempt to retry. So what traditionally happens, you make a request, something fails. You don't just give up. You perhaps retry once or retry a second time. So if you're not using a library, you'll generally have custom logic for this. And we're trying to look at the solution that we could build without integrating any libraries at this point. So you'd have custom logic for a retry. If you got a happy path, you'd have the data response back from the promise. You take the data in whatever format it is, and you'd map it in a way that's suitable for the props you'll send to the chart component. You'll set it in state. Your UI will re-render. And then let's say you have another piece of UI which you can perform an action on, a button somewhere. And when you click that button that's linked to state, it sends another state dispatch. And if you don't organize your state correctly, a React state change can cause a re-render of a component that can cause a refetch of the data. And if you're doing 5 parallel API requests and you're repeatedly refetching that due to other states changing in the application that are not related to the graph that you're seeing, you risk timing out the server with too many requests and receiving a 429. So that's a little bit of a problem. We're going to see what that looks like in terms of code and then with a visual UI example. So this is what the code may look like. You may create a hook called useFetchData. You may have a function that gets fake data. Right now, this is getting fake data from a fake server that I built. And then once it receives that, it's going to map the data client side. So it's going to get the birthdays by month. It's going to do a little bit of work there. It's then going to map it to the chart data, and then it's going to set the data in state. So let's look at a demo and see what this looks like when we bring it all together. So we've got a chart, really basic one, and it's taking a little bit of time to load because we're making a lot of requests to server and we're getting back a lot of information. That's not a fantastic experience. We go look at the network tab and we go and click a hide and show button, which toggles state. Because the state was not correctly set up, you could actually impact the chart UI that was rendered. And then when it appears back and it's loaded onto the DOM, it triggers a side effect, which then starts to fetch again, which is not optimal because the data is not something that needed updating. You don't have new users added every single second. So you don't need to update your data constantly. You can actually cache it at some point in time, but that's not something we're doing. So because our state is not set up well, it's a little bit problematic. Now, if you had a look at the network requests, maybe you noticed one thing. The next slide shows that to fetch all that data, 5 times 1,000, 5,000 data points with a lot of key value pairs in there that we did not need. Actually, 2.3 megabytes of a payload was received. That's massive, especially if you're querying that in countries where you've got limited data bandwidth, where it's going to take even longer if you don't have, a Wi-Fi connection or so on and so forth, or if you're on a data roaming package, using up a lot of that package just to load a simple website. Sometimes those things need to be optimized. And by my calculations, around about 73% of the data we received is actually unused and unnecessary to be able to show the chart that we want to. So we need to rethink the solution because we're not really showing something optimal. So a couple of key factors. Custom retry. If we developed a custom function to manage retries, it needs testing, it needs maintenance, it's subject to bugs. Retries, we don't want to reinvent the wheel. There are a lot of libraries that do that. So generally, they'll fit a solution. Caching, we've got none by default, and there's no reason why we can't cache that data. So we're going to look at that in a little bit. State, complex to manage state globally and sync the data with staleness. So with data staleness. And so if you don't set up your React component structure and hierarchy correctly, you may have parents that affect child components that cause unnecessary re-renders and side effects that increase the amount of data you're fetching when you don't need to. And then we're doing data mapping, a lot of effort on the client side. And if this calculation is really complex, which in this case it's not necessarily, you may need to memorize, which is additional overhead. And again, we're not optimizing the payload for state and caching. So introducing the backend for frontend pattern, that's what it stands for. It's not best friend forever. It's otherwise known as the transformation bridge or the aggregation proxy. And a couple of key points on this. So it adds a little bit of adaptability to platform requirements. The BFF pattern allows developers to create a backend service, a proxy that caters to each platform's unique requirements. So let's say you've got a backend and then you've got a web UI, you've got a mobile UI. You can have a proxy that sits in the middle, whether it's a Node.js service you spin up or a NextJs API endpoint that takes the data from an endpoint that you can't control. You can then go manipulate the way you want to, and then it finally arrives on your client side. So whatever the data format you need, whatever the interaction patterns are, you can have a more efficient resource usage. You decouple the concerns. So instead of doing all the logic on the front end, all the calculation on the front end, you delegate the data aggregation. So the calculation of the birthdays, the chart data, and all that transformation task it's being taken care of on the proxy, which then if your front end's doing a lot of work, a lot of other calculations, you're saving up the amount of work that it's doing. So you're able to offload a couple of tasks somewhere else and really keep that separation of concerns. Then you optimize for performance. You can dedicate a backend for each front end. You can even have a couple of your team members work on that particular proxy to do additional caching optimizations, reduce latency, manage reducing the payload size, and just overall increase performance. You're not doing all that work on the client side. So what could we potentially do? We can take that larger payload we're receiving and we can condense it down to the minimum that we need. And there's a lot of key value pairs that we shrunk right there. And so what's changed in our architectural diagram if we do that, if we bring in this BFF pattern? So if we do this, we only make one API request to a Next.js handler on the client side. So instead of 5, we initiate our loading state, and now our Next.js handler or whatever microservice that sits in the middle is going to be the one that makes the 5 parallel API requests. It handles then the retry logic if need be. And if you've got a happy path, you receive the data, you map that on the server, and the client only receives the minimum amount of your payload in order to be able to display the UI that you want. Send the data to the client, you set it in state, but then we're still subject to the same problem where if you have any other state updates that happen that are not related, you may risk re-triggering the entire flow. And so the code that we wrote before may be optimized to just this. We're going to just fetch from our proxy, and we don't need to do any of the calculations on our end. That's a little bit cleaner in terms of the code. We don't have to do any complications on the client side. So key factors, there's failure isolation here. So you're making just a single client-side request rather than managing multiple. Let the server do that. Clear code-based management, payload optimization, and then you're able to do the data mapping on the proxy. We're going to go for a second demo, and we're going to see how this affects your application. And it already loads a little bit faster, and we'll see why. We'll dig into the network tab. If we refresh, you'll see that only one API request is made, and the data comes back exactly the way we need it for the chart. And we're only loading 666 bytes versus what we were before, which is a 99.9% payload reduction. Now, this is a scenario that was designed to prove a point in this talk. You're not going to see a 99.9% payload reduction in your production applications or all the other projects that you work on. So you will see some optimization, but this is a little bit of an exaggerated case. Bring in React Query, or otherwise known now as TanStack Query, which is the powerful asynchronous state management library. And I'm not going to go through all the features. That's something you can look up on the website yourself, but we're going to dig in a little bit to how this changes our architecture if we bring it in. So we know that we have a user interface. We're making one API request to Next.js from Next.js to the handler, and now we're using React Query to manage that. So instead of us using a useState or any other state management library to handle the loading state, React Query takes care of that for us. So we don't care about loading. Then our proxy is going to make still 5 API requests. Nothing changes. If something fails and it comes back as a 500, we return an error code to the client, and we attempt to retry. And React Query handles that retry on our behalf. So we don't have to have any retry logic. We don't have to have anything that's tested on our side. We don't have to have anything that may be maintained or subject to bugs. We are offloading all that retry mechanism to the React Query library. And it's able to do 10 retries if you want 3. You can configure those, and you can even configure exponential backoff, which is a strategy where instead of doing, if you need to do 3 retries, you do one after the other immediately. You're able to stagger those off, and exponential backoff allows you to do the first retry after 1 second, the second retry after 2 seconds, and 3 seconds, and allows to give more grace for the server to recover itself before it returns anything. And that adds a bit more resilience to the application. Now, moving back to if we get to the happy path, we do the same thing. We map the data on the server. We send it to the client. React Query derives the state from the response. We render the UI. And now if a React state change happens, React Query actually checks its in-memory cache, or we can configure offline cache. If there's a cache hit, we go straight to rendering the UI, and we have no side effects. We're not redoing all the requests. It is a cache hit, or if it's stale, like it's been sitting for 5 minutes and we declare after 5 minutes the data is no longer useful for us, we want to have a fresh set of data, then we restart the journey and we're reducing the load and impact on that server. So the code moved from our custom hook that we created, and now we're using use query, which is a hook that comes directly from the React Query library, and we simplify that code quite a bit. What's interesting also, even if we did custom cache management with local storage in our custom solution, one of the really complicated things with that is managing query parameters with caching. So you can see that there are query keys over here that we put to React Query. For the same endpoint, I may have different query keys that I provide. So I may fetch with a quantity of 5 this time, another time a quantity of 10, a quantity of 1, and this allows you to store cache for every single query parameter combination for a particular endpoint. That's also a lot easier to manage. So quickly to wrap this up, key factors. With a library, we have all these things handled for us. It makes life a lot easier. We've got caching, we limit re-renders, and we add a little bit of out-of-the-box configurable resilience. But there's one more thing we can do, and we can bring this over to the server. So now we're still doing all this work on the client. We're hitting that proxy server. But in Next.js, you're actually allowed to pre-render or pre-fetch a couple of things before it sends the skeleton HTML over to your client and starts to hydrate with all the JavaScript. So this time, instead of a UI, we've actually got a server. So we're on the server, and the server will pre-fetch and attempt to pre-fetch the data from the proxy. Then it comes back with the data. Let's say it's the happy path. It will then send that frozen, dehydrated state over to the client side, immediately hydrate with the React query, and then you actually won't even have any loading state initially. You'll directly render a UI. So this way, you can actually get an even faster response. However, in scenarios like this, some more problems come into play. You actually have an issue where if your request takes too long to come back, your UI will actually never receive its initial HTML. Your browser will never receive it. So if your request is taking 2 seconds to arrive, your user will wait 2 seconds on a blank page before actually seeing anything. This is where we can implement a timeout control where, okay, I'm trying in an optimal scenario to get the information and prefetch it as soon as possible. Let's say it comes back in 10 milliseconds, fantastic. But if it takes over 1,000 milliseconds, bail. Don't bother making that optimization and try to show the UI, hydrate it, and continue fetching on the client side. So over here, you can build your system to be able to, in its most ideal scenario, fetch the data as fast as possible. But then if something goes wrong or it takes too long, you have backups and you have fallbacks that happen, and then everything tries to recover on the client side. So it adds a lot of resilience. And this is what the code looks like to be able to do so. I'm not going to dig too much into that. I'm happy to share the slides later on. But I also appreciate I'm running out of time slowly, and Simon might stop me. So what happens with the server side? Now that we're moving things to the server side, we're able to prefetch. So we're reducing the UI delay. So we're showing things a little bit sooner. We're also load balancing a little bit. So if your client's going to be making a lot of requests, you can make a couple on the server beforehand so that you're reducing the amount of work that the client's doing at a network level too. You also have data recovery strategies, which means that if your server fails to prefetch and times out, your client side is going to start recovering for you. And then also another concept that you can introduce is query criticality, which is if on the server I'm trying to fetch a set of data and it doesn't arrive, and I deem that it's not critical to show to my UI, you can just bail and fetch that data in a deprioritized manner on the client side. So an example of this may be that we have the chart data that we're showing. What's crucial for the chart data is to receive back all that data from the 5,000 users, and that's a critical query. If it's critical and I'm trying to prefetch it and the data doesn't come back, I can show some error states on my UI. If I mark it as an optional query and the query is not crucial to show to my UI, I can say that bail the request, show the UI, and you can attempt to later on try to refetch the data because it's not something I need to immediately show to the users. So you can decide what's more important to fetch and what's less important to fetch. And we're going to go for a final demo to see how this all ties together and hopefully it makes sense. So this time we're reloading and it comes really, really fast. We click the hide and show button, and because everything's being cached, we show things nearly immediately because it's deriving from the cache and not doing another fetch. We're showing also example of how the timeouts work. So over here, there was no timeout that there was a timeout that initiated. The request took too long to come back. I'll quickly replay that actually. the request took too long to come back, so it actually tried to recover on the client side. But when it happens in an ideal scenario, like the first time, you can see that there was no client-side request initially. So over here, everything was prefetched from the server. If we look later on and where we adjusted the timeout, I'll look a little bit in the code. We adjusted the timeout. It has to come back within 500 milliseconds, I think we said. Let me play that from here, 500 milliseconds. The request isn't able to do that. So now the application bails and tries to recover with the loading state on the client side. So this is making our application a lot faster, a lot more responsive, a lot more resilient, and optimized to make sure it's doing the least amount of requests to show the UI that we want to show. And that's pretty much it. That's a lot to